Hello, welcome to 3.5, Modeling with Nonlinear Regression. Now, before we get any further, I just want to pause and say, hopefully you watched the video about how to type in these types of functions in your graphing calculator. Even though it only showed you not every single function, but all the different regressions you can find um, where you start off, um, right next to where you'd find exponential regression, logarithmic regression, etc., etc. They're all like right there. Okay. So my hope with this video is that you have your calculator and you are doing this um, as we go through these examples, and that you are able to practice and you have a better grasp of typing these in, so that when it comes to the test, you're not asking, how do I do this in your graphing calculator? No, you should know, okay? Because you're watching this video, you're practicing. You saw the previous video um, that I explained to you, and we do more in class, and you're super set and ready to go. So we have this example here. The growth of a culture of bacteria is shown in the table below. Use the exponential regression to model the data. Then use your model to predict how many bacteria there will be after 24 hours. Okay. So first we're finding the equation. So you have this will be under your L1, this will be under your L2. Um, there's always one or two students in class that for whatever reason their lists are all messed up. Talk to me in class if you're one of those people. I'll try to get you squared away so that you can properly type things in. So L1, L2, we're set. And then you go to your exponential regression, and you should have an equation that is b of t. If you didn't use b, that's fine. Equals 400 parentheses 1.19 to the power of t. That's the equation you should get. And that's asking you how many bacteria will be there after 24 hours. Your time is in hours because that's what's given to you right here. So we can just plug in 24 straight up, do that in your calculator, and you should get an output of 26,013 bacteria. A lot of bacteria grew, huh? Pretty wild. Next example, we have a group of students who studied photograph for 30 seconds. Being one day later, a test was given each day to test their memory of the photograph. The average score each day is shown in the table. Use logarithmic regression to model the data. A little hit into also, please make sure you read the problem, okay? It'll tell you what regression to use, okay? There are problems in the book where it's like, guess what? Which one's best? I'm not going to do it to you. It's going to straight up say, and then you're going to type it in, and voila. Although a good skill that we're going to talk about in class, I won't make you guess, but we should be able to plot this on your graph and be like, oh, this one makes more sense. Oh, that one makes more sense. This looks like this graph. Okay, so we should be able to recognize that with your data. Anywho, so you type these in, L1, L2, respectively, and what are you going to get? You're going to get the function S of t equals 73.1 minus 7.31 ln of t. So then after 2 weeks, that's 14 days. Be careful you don't plug it in 2. You get the wrong answer. You'd be like, what? That doesn't make sense. So remember, this is in days. Okay, so make sure you're reading the problem able to figure that out. So it's in after 2 weeks. So you're going to put 14 in for t. When you put 14 in for t, you're going to get 53.8%. Last function we're going to go through in this section, and this will be it. Logistic growth function. Okay. So these are good for whenever you have a problem like population in some instances, right? Because if you look, let's say a classroom, our classroom size could grow exponentially, right? But then eventually we're going to run out of room for people to be in there. Okay. So that's going to happen in certain cases. And that's where a logistic growth function is. In this equation right here, all the values are positive, and also C is a special name, okay? C is our limit for growth. Because with how this equation is set up, no matter what we put into these values down below, it will not ever be, your output will never be more than what C is. Okay. So we have an example down here, L1, L2 for ads and percent people. I'm going to read to you what the problem actually says. In advertising, the number of television ads for a certain product affects the percentage of people who purchase the product as shown in the table below. Use logistic regression to find a logistic growth function to model the data. Then use your model to predict the limit to which the percentage of people who will purchase the product. Okay, so we have a table, L1, L2. So go type it in. The function you'll get is P of X is equal to 55.86 over 1 plus 50.24 e to the negative 0.064x. Okay. So it says, as I said before, use your model to predict the limit to the percentage of people who will purchase this product. Okay. So your limit is going to be whatever this top number is. Okay, it's a simple enough number. Okay, because no matter what I put into X, it will never be more than that. But also to recognize that even though this is our limit, we don't know what's going to happen if there's 115 ads or 100 or however many ads, right? Um, but the predicted amount is going to be about 56% would be a good answer, or if you want to go exact, 55.86%. That's going to be your limit. Okay, it's never if you put this in your graphing calculator, it's never ever going to be more than that value. And if you do graph it, it's going to be something neat. Okay, the graphs of these normally look like this. They hug, and then all of a sudden, boom, goes up, and then stops going up. Okay, and it'll be some form of this, even though, as you know, my art skills on this drawing it is not the best, but it will look something like this no matter what your logistic function is. I appreciate you. Thank you for watching, and we'll see you in class. Bye bye now.